So we'll start the class. So very good day to everybody. This is using Python in multimedia and gaming machines. And in today's class, we'll discuss about physics-based simulations and scene graphs. Okay. So this is especially for you, my dear students and young researchers. And you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. Right. So in this class, we'll discuss about physically based animation. Maybe what you try to do, the animation will be seeing, and the difference between PBA, physically based animation, and of course traditional keyframe animation. What are the basic mechanism in the search-based methods? What do you call by RL, reinforcement learning? The agent environment interaction in the reinforcement learning, the whole animation pipeline using physically based animation. What are the basic structure of the scene graph, the scene graph of the object model? Then we'll have a file link joint chain and the scene graph, rotational transformation. Maybe if you try to rotate, how you will be explicitly viewing the 3D view. So that we'll be discussing. The general transformation of the model, showing the translational and rotational parameters. Okay. So we have also got composite transformation as well. Okay. So I hope that you have all completed your environment work and have got your marks even. So at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topic. So this is physically based animation. Actually, it's an animation. Okay. So it refers to the area in the computer graphics where you try to aim to generate physically plausible animations using AI, artificial intelligence. So this one, it will be, walking, maybe some balls will be coming, it will be hitting. Okay, so that it will be going continuously. Okay, so that's programmed by using AI. So the animations were usually played using the virtual character. It's a virtual character in 2D or maybe 3D simulated environment. So the example of the recent state of the art result using physically based animation is given. Okay, so that is how you will explicitly define when we walk. Okay, so that maybe the block will hit and again it will go on to run. Okay, so one of the main differences between PBA and of course the traditional keyframe animation is that PBA can dynamically adjust to the changes in the environment. Okay, so that is advantage. But keyframe animation, it's static, non-responsive, and it should be handled carefully. Otherwise, it will result in unnatural movements. Even in the game, if you can see, maybe one type of animal is falling from the top to the bottom. So very realistic will be. Sometimes very low quality games. Sometimes sometimes a big thing happens like this. Suddenly it stops. You cannot do anything. You have to only quit. Okay. So that is not possible with the PBA. So we'll have search-based methods. Okay, so it's a classic yet much more powerful class of approaches for solving this physically based animation. So this one you will be using search methods for optimizing the movements. So the idea is very simple. Okay, so you have to generate a number of action sequences and you have to evaluate them using forward simulation and you have to compute the cost function. Finally, you have to choose the action sequence that is going to minimize the cost function. So we'll have the process. Okay, so this is going to have the basic mechanism in the search based methods. Okay, so here the objective is to control the object from the left side, okay, to the green circle here in the right. So the projector is, you will show it in the blue color, okay, and gray lines are nothing but the randomly generated trajectories or maybe path. So after computing the cost function for all the generated trajectories, the trajectories with the minimal cost would be shown in the black color. That is the solution. So because of the search methods with the PBA advantage, you can go on to find the solution. So the resulting animation would be, it's much more clear cut. Okay, so the box is also very clear cut. The mosaic pattern also is very clear. Okay, so that is how very clearly it will be, walking. Okay, even when the blocks hit, it will be, still holding on to and it will be running. So that is the parameterized controller for synthesizing the movements. Then we have RL. reinforcement learning. Okay, so it's a topic of ML, machine learning. We will have like computational approach to learn from the interaction. So as you see, this is the agent, this is the environment. So action means you do some action, okay, like licking the feet or maybe something, you get the reward, and that will also understand, train the observations. Okay, so if we lick the feet, one reward will come, or maybe if you help Saripo, immediately I will get reward. So that observation I am trying to get. Okay, so the basic definition of reinforcement learning is all about agent that has interactions with the environment, and you have to maximize that accumulated reward in a very small time period. Okay, so in each step, in each of the time step, the agent observes the current state and of course takes an action. Okay, suppose there is a dog, okay, like you are a master. Okay, suppose if you are angry means what the dog will do, hello, not like that. Okay, so it will immediately, it will go somewhere angry, so it will go like that. You are in a very good mood, hello puppy, come here, immediately go and do like this. So it is observing. Okay, that is the work of the agent in the machine learning. It is observing the inputs and it will be processing the outputs. So after that, the agent observes a scalar reward along with the observations of the new state. So the aim is to optimize the agent such that it receives the maximum possible reward by taking the optimal actions. So here with the case of agent, okay, so it will go to the environment, the action, okay, in the time at. Okay, so we'll have the state st, okay, st plus 1, reward rt plus 1. So here RL, reinforcement learning, has been used over the years because of the results of the DRL, deep reinforcement learning, in the Atari games or maybe game of Go. So maybe if you have Googled or maybe in YouTube, you can find this one. So that is based on the reinforcement learning. So we'll have several breakthroughs, especially for the continuous control. So one of the state of the art methods is this one. Okay, like we'll have this one, okay, image. So correspondingly a virtual model. So somebody who's standing like this, so that also will have the virtual model. Okay, so we'll have different postures. Okay, so this is the pipeline that consists of 3 stages. We'll have pose estimation, motion reconstruction, and motion imitation. What we try to do, that also we'll try to do. Okay, so the input video is actually processed by the pose estimation stage, which predicts the pose of the actor in each of the particular frame. Next, you will go for motion reconstruction, that is going to consolidate, add up all the pose predictions into a reference motion, and you are going to fix up for the artifacts in order to reduce the noise that have been introduced by the pose prediction. Finally, reference motion. So that is passed on to the motion imitation stage, where a simulated character is trained in order to imitate the motion using the reinforcement learning. So which of these games use the physically based animation? So because of the higher requirements in the computational resources, PBA, physically based animation, is not used in the animation pipeline of the video games. Okay, but it is interesting that almost any game that has intensive animation system uses maybe at least few PBA techniques. So maybe you will have FIFA game, okay, PAS, Assassin's Creed. So these games will be using PBA, physically based animation. So this is actually an animation using the physically based animation. So it will come here and it will hit. It cannot hit 2 times, 3 times, and afterwards the 3rd time it will hit means the blocks all will fall down. Okay, so that is the animation. Okay, so putting this big game titles aside, there are also very few indie games, okay, so that have implemented animation pipeline solely using the PBA. Okay, so we have like QWOP, Tori Bash. That's very small game, successful game. Okay, so maybe suppose you are free, you are working too much. Okay, 15 minutes, 20 minutes we will play game. Small game. That's based on the animation. So you can find a lot of gameplay videos in the YouTube as well, and of course you can see this animation video in the Tori Bash. You can see Google, YouTube, even you can see very small game you can try. Okay. Then the second part of today's class will have the scene graph. So it's a data structure that you will use it to represent hierarchical relationship between transformations applied to the objects in the 3D scene, three-dimensional scene. So you can use it in the applications like acceleration and maybe rendering algorithms as well. We discussed about rendering. Okay. So scene graph, you are going to organize visual attributes, bounding volumes, and of course animations in the hierarchy, in the collection of the objects. Okay. So any scene related information that can be organized in a hierarchical fashion can be stored in the scene graph. Okay. So this is how you try to conveniently represent local groups of objects using the spatial positions or maybe attributes. So we'll have the basic structure of the scene graph. So the structure and contents of the scene graph depends on the type of the information it is going to store or maybe the operations that it is used for. Okay. So we'll consider a simple tree structure. We'll be having three types of nodes. So we'll have the root node of the tree, okay, which represents the whole collection of the objects in the 3D scene. We call this one node 1. We call this node as the world or maybe virtual universe. Okay, so the root node is the special type of the group node. Then you have group node. It's an internal node of the tree. It will contain like children, okay, number of children, and it will be representing a logical grouping of the objects. So group node will not be storing any geometrical data, but it will be using only semantic information like transformation or maybe visibility attributes that is going to apply for the entire group. So every leaf node which will be representing either object or maybe small part of the object and will be maintaining the geometrical information in addition to the semantic information. Okay. So camera, light sources, that is how you represent by the leaf nodes. Okay. So world, object, group. So within the group we'll have maybe group, another group, object, object, object. So you'll see all these one with the leaves. So this is the scene graph of the object model. So this is an example of the model which has 4 connected parts that moves relative to each other. So base, part 1, part 2, part 3. Okay, maybe like this one. Okay, like one thing is there that is actually moving. Maybe it is fitted. Let us take in the case. Small toys, if you can see like this, you can make into movable. Okay. Then this is a scene graph of the object model. So here we'll have complete world, then group 1. So within the group 1, you'll have one base, part 1, then group 2. Within the group 2, again, part 2, part 3. Okay, so that you'll be having several parts in the scene graph. So we'll understand the tree structure of the scene graph. Tree structure of the scene graph has a property associated with the group node to be inherited by all of its child nodes. So whatever the parent follows, child also will try to follow. Okay. Right. So for example, a transformation applied to the group node can also be considered as applied to the children even. Okay. So similarly, a bounding volume, if attached to that particular group node, will also be representing the overall bounding volume for the whole collection of the child nodes. Then the scene graph, that is how you try to animate a composite object. We have like several parts that will also move, and if the parts are physically connected to each other, they will all simultaneously will move, because this part moves means this part will also move. Okay. So this is a typical example of the object. We'll have the articulated character model. So we'll illustrate the formation of the scene graph using a simple model. We'll have 4 connected parts: base, part 1, part 2, part 3. Okay. So as I told you, link 1, link 2, link 3, link 4, link 5. If I try to move this link 2, immediately link 3, link 4, link 5 will move. And this is the scene graph. Okay. So this is a 5 link joint chain: world, link 1, group 1. Okay. Then group 1, link 2, group 2. Then group 2, link 3, group 3. Group 3, link 4, group 4. And group 4, link 5. So that is all are interconnected. One moves means everything will be moving. Okay. So it's a 5 link joint chain. Fine. So you see in the diagram, the whole model, you are going to subdivide it into 3 logical parts. Part 1, base. Then you have the subgroup, which is group 2. To which part 3 and part 2 and part 3 will belong to. Okay. So we can assign transformation parameters to the individual nodes of the scene graph in such a way that the parts can actually rotate with relative to each other. At the same time, it will be connected as the single animatable object. So maybe if you are going to go for any maybe Blender platform or maybe something that is something you have to move means, so one part will move means subsequently connected to it will be moving. Okay. So we consider a closely related object model, joint chain, consisting of 5 links. Okay. So joint chains are similar to what we use in the robotics, and of course articulated models in the computer graphics. So scene graph, it's a hierarchical subdivision of the model where at the first level the whole object belongs to the single group world. Then we have rotational transformation. At the next level of subdivision we have link 1 and then subgroup, which is group 1. Okay, so that will be containing the remaining links. So maybe one rotation you are going to change. Okay, rotational transformation applied to group 1 will be affecting all the members of the group because all are connected. Okay, so it may appear that the group 4 is redundant because it has only one child, so that it will not be affected. So the node that is useful to provide a clear separation between the initial transformation to the link 5 in its own coordinate system, and of course the transformation applied related to the link 4 frame. So we'll also maybe add a camera as an object belonging to group 4. So this is the rotational transformation. Maybe it will have like alpha, theta, okay, gamma, so that it will be affecting the remaining parts as well. So this is the transformation hierarchy. So transformation applied to one part of the object is going to cascade the transformation applied to the adjacent interconnected parts. So a change in the orientation of part 2 of the model in the diagram also will be affecting part 3. So you can make these dependencies convert into hierarchical representations in the scene graphs. So we'll see 3 examples: the model of the mechanical part, then an articulated character model, and a system, a small planetary system. Okay, so here if you can see, okay, we'll have the base part 1, part 2, part 3. So this, it will be having a model with the theta, a del 2, and here with regards to perpendicular we'll have x, y, 0, the distance a. Okay, so this is actually the general transformation of the model, which shows translational and of course rotational parameters. So first we will see the mechanical part. So the general 2D transformation of the model in the diagram will see the translational as well as rotational parameters. So we'll use T of A to denote the translation of the vector A, and of course R of 6 to denote the anti-clockwise rotation through the angle 6. So we'll see that the joint angles like 1i, 1, 2, 1, 3. So that will be having the relative angles of the rotation of one part with respect to another. So maybe in order to follow this transformation hierarchy, we have to consider first the transformation of each of the link from its own local coordinate frame to the coordinate frame of the group. So the sequence in which the transformation you are trying to apply is actually shown. So the transformations are applied from the leaf nodes to the root of the scene graph. Okay, so that is how you try to rotate the part 3 by an angle 30. Then you are going to translate along the length of the part 2 by some vector d3. Okay, so this composite transformation will be having the matrix like it will be in the matrix format TD3 R13. Okay, so group 2 will be having part 2, and that will be having a transformed version of the part 3. So both part 2 and part 3 are nothing what you have to transform to the coordinate space of the group 2. Okay, so which means that any rotational transformation of part 2 is definitely applied to the group 2 as well. Okay, so here the transformation matrix TD2 and R12 is going to convert the points from the coordinate system of the group 2 to the parent group. What is the parent group? It is actually group 1. So we will see the scene graph with the transformation matrices added to the tree nodes. Okay, so we see that every node transformation we follow a hierarchy. What the child? Parent only. From the parent only it has come. Okay, so at the leaf node a transformation converts vertices from the local coordinates space of the object to the parent's coordinate space. So maybe if the object node has this identity transformation, maybe I, it shows that the parent node has the same coordinate reference frame as that of the object node. So which means that any transformation applied to that node is actually applied to the parent node given. So the transformations applied to the base are actually applied to group 1, and they indirectly affect the transformation of each of the group 1's child nodes as well. So this is the thing. We'll have part 3. Okay, so that's being transformed TD3 R sigma 3 to group 2. So that is being applied to group 2 as well. Okay, so we'll have the movable. Then TD2 R sigma 2. So that applies to group 1. Okay, so we'll have the base part 1 group 1, everything we will be having. Okay, so that is transformed T of A R of theta. So this is to the whole world. So whatever maybe we, for example, this one we try to move, this one we try to move, then this one we try to move, 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 and like this. So everything will be moving, everything is being connected. Okay, so one thing you apply means, so I cannot do like this alone. So do like this. For every part it will be moving. So okay, so that is the composite transformation. So scene graphs with transformation matrices attached to the nodes, we'll see world, group 1, part 1, base, identity. Base is nothing but identity, group 2. So the part 1 will have transformation T of D1 R of sigma 1. Group 2 will have T of D2 R of sigma 2. So it will be having part 2, which is identity, and part 3 T of D3 R of sigma 3. So this is the scene graph with transformation matrices attached to the nodes. So this is complete the scene graph of the basic articulated character model. From the world it will go to group 1, T of V0 R of sigma Z, okay, R of sigma or maybe the omega, whatever you call it. Okay, so psi or maybe sigma Y, R of sigma X. Okay, from that it will go to the torso and head, maybe something in the head, something in the leg, so that it will be changing. Okay, so maybe torso you will see. Okay, this I am talking about. So group 2, group 3, group 4, group 5, left lower arm, left upper arm. Okay, right lower arm, right upper arm. Okay, left lower leg, left upper leg, right lower leg, right upper leg. So maybe we will have the identity matrix: left upper arm identity, right upper arm identity, left upper leg identity, right upper leg identity. So here all will have the transformation vector, so that it will be changing. Maybe some part it will be fixed, some part will be movable, so that we will be making the translational vectors.